Okay, in this video we'll be looking at the sine rule without proof, but we'll just aim to get a feel for what it's trying to say and to demonstrate using it a couple of times. So here's a triangle, and we're going to start by looking at this little angle here. Because this pink angle is the smallest angle in the triangle, naturally, the pink side directly across from it here will also be the shortest side. Likewise, if we look at this big blue angle here, because this is the largest angle in the triangle, naturally, the blue side directly across from it here will also be the longest side. And again, for the remaining green angle, its size is somewhere in between the other two, and so the green side directly across from it will also be somewhere between the lengths of the other two sides. Okay, so there's this natural relationship, some kind of weird proportion thing happening between every side length and its opposite angle. And because of this, we tend to name the sides and angles accordingly. And here's how you'll find these equations written on your reference sheet. Side little a, we say, is opposite angle big A. Side little b is opposite angle big B, and side little c is opposite angle big C. Okay, those are the letters we often use, and those are the letters you'll see on your reference sheet. Okay, then to express this relationship between every side and its opposite angle, this strange proportion thing happening, we form a fraction comparing a side length with the sine of its opposite angle. So here we have little a over sine big A. And that relationship must be the same across all three sides. Okay, so this must be equal to little b over sine big B, and that will again be equal to little c over sine big C. That's why we call it the sine rule. There's all these signs there, okay? Now, of course, with this equation here, we can turn everything upside down, and that's still the same equation, just written differently. But this puts all the angles on top. Okay, there's no real difference, but you might see it written this way as well. And two things to note in practice. Okay, first, we only really ever compare two pairs of these at a time. Okay, there's rarely a need to involve all three sides and all three angles. Okay, practically, all the use comes from just comparing two pairs of sides and their opposite angles. Okay, but it is helpful to have seen and to know that you are allowed to choose any two pairs you want. Okay, the only thing is that you must be matching each side with its opposite angle. So if I'm going to use the blue side, I need to compare that with the big blue angle here. And if I'm going to use the green side, I need to compare it with the green angle here. Secondly, there are these two equivalent forms, and you're free to either put the sides on top or the angles on top. Okay, algebraically, though, it's just easier to put the thing we're trying to calculate on top, as we'll see in a moment. Okay. Honestly though, I never find myself actually writing this formula out ever, okay? I'm just showing you what it looks like because, again, that's how it will often appear in reference sheets and textbooks and things like that. But the main idea is what we've said about matching sides with their opposite angles. Okay, so here's how it really looks in action. We have a triangle here, and we want to calculate the length of side x. Because we want a side length x, we're going to put the x on top. And we need to compare that with the sine of its opposite angle, the 43 degrees. And so we must use 43 degrees downstairs here in the sine. Then the other comparison should be made between the side and angle we know. So the 4 with the 67 degrees. And so we put that fraction in, 4 over 67 degrees. Notice because we put the side length on top for the pink ones, we have to do the same thing for the blue ones. Okay, so now to get the x by itself, we just need to multiply that right-hand side by sine 43 degrees, and we get about 2.96, and we're done. To finish, we'll do an example of finding an angle. So here's another triangle, and this time we want to find the angle theta. So it must be compared with its opposite side. Hopefully we're getting the hang of this now, the 4.9 here. So we can form a fraction with sine theta over 4.9. This time, we're putting the angle on top because we want to work out an angle. Okay, so that just makes the equation a little bit simpler to solve. Then the other comparison can be made between the 35-degree angle and its opposite side, the 3. So we put sine 35 degrees over 3 on the right. Now to get sine theta by itself, we just need to multiply the right-hand side by 4.9. And we get something like 0.936 something something something, okay? But to get the theta by itself, all we do is the backwards sign of that answer, the shift sign thing, and that gives us 70 degrees. Okay, and we'd be finished here. It is worth pointing out, though, that if in the question we somehow knew it was told to us that theta was actually an obtuse angle for some reason, okay, then the triangle could well look like this. And it's important to see that none of the other numbers needed to change. So the pink side is still 3, the pink angle is still 35 degrees, and the green side is still 4.9. And that means all of our working is exactly the same. But if we know that theta is meant to be obtuse, then rather than just take the 70 degrees the calculator gave us, we know that sine has another option for achieving that same 0.936 blah 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 number, and that comes from doing 180 minus the 70. Okay, and that would be 110 degrees. So if theta was known to be acute, the answer would be 70 degrees. But if it was known to be obtuse, we would have to subtract that answer from 180 to get 110 degrees. Okay, so read the requirements of anything you come across really carefully to know which one to use. So that's all. Thanks for watching. See you next time.